So what's going to happen if we take a solid chunk of this calcium hydroxide solid and introduce it into this aqueous solution? Well, we know it's going to dissolve. It's going to dissolve in this aqueous solution. So that makes sense. And when it dissolves, we can see due to the stoichiometry in this molecule, essentially it's going to produce, for every one molecule of the solid that dissolves, it's going to create one calcium ion and two hydroxide ions. So we've done it. We've added this solid into the solution, and now the solid's going to start to dissolve. And if we wait, we know it's going to dissolve, and eventually it's going to reach an equilibrium. This solid's going to dissolve, it's going to produce some of these ions, and if we wait for a long time, eventually it's going to reach an equilibrium with a certain concentration of calcium ions and a certain concentration of hydroxide in the solution. So we know we can represent that with one of these equilibrium equations. We know if we have this reaction, we enter this solid, we let it react through this reaction, and we let it reach equilibrium. Eventually it'll reach equilibrium concentrations, and we plug in those equilibrium concentrations and we get the KQ of this reaction. However, because really with these equilibrium constants we're interested in mole fractions, and because this is a solid we ignore it, but it's a little complicating, but in reality we just ignore the solid in this equilibrium equation. So really we would just ignore the solid. So the equilibrium equation would reduce to this. And instead of calling it the KQ, we call it the KSP. Really it's just the equilibrium constant of a solubility equation. But again, so remember what's going on. We introduce the solid into the solution and we let it react. We let it dissolve. It dissolves, forming these ions, and then eventually it'll reach equilibrium. Eventually it'll reach equilibrium with these equilibrium concentrations. And if we took those concentrations at equilibrium and plug them into this equation, we'll get the KSP, the KQ of this reaction. And this reaction happens to have a KSP of roughly around 6.2 times 10 to the negative 6. So what does that mean? That means whenever you take a chunk of calcium hydroxide and enter it into a solution, it's going to dissolve. It's going to reach equilibrium. And if you take those equilibrium concentrations and plug them into this equation, it will always spit out the KSP, which will be constant and will always equal 6.2 times 10 to the negative 6, assuming that the temperature is constant. But again, we know that's how these KQs work. Essentially, we let this reaction reach equilibrium, we plug in those equilibrium concentrations, and it'll always equal this KSP. For this reaction, it'll always equal 6.2 times 10 to the negative 6. And really what's going on is, again, this solid, it dissolves, it reaches equilibrium, and we have equilibrium concentrations. But really those equilibrium concentrations are the saturation concentrations. It's saturated. It kept dissolving. The solid kept dissolving. It kept dissolving, forming these ions. But eventually it's saturated. These ions have become saturated in the solution. And once these ions we've dissolved the max amount and these ions have become saturated in the solution, we've reached equilibrium. So really, these concentrations are saturation concentrations. And again, so that's what's going on. But now let's introduce the ion product. So what is the ion product? Well, if the KSP is the KQ, the equilibrium constant, then the ion product is the reaction quotient. They're essentially analogous. It's the same idea. This ion product, really you could just call it the reaction quotient. They're essentially the exact same thing. So therefore, we know once these concentrations reach equilibrium, we plug them in and they'll equal this KSP. However, what if we're not at equilibrium? What if we put in this metal, then it starts dissolving, but we haven't reached equilibrium yet? We plug in those concentrations and that gives us our ion product. So let's do an example. Let's say we just put a chunk of this calcium hydroxide in and it starts dissolving. And we wait 1 second. And 1 second later, the concentration of calcium, let's say the concentration of calcium happens to be 1 times 10 to the negative 4. And let's say 1 second later, the concentration of hydroxide happens to be 1 times 10 to the negative 8. So those are our current concentrations. So if we take those current concentrations, plug them into this equation, we'll get our ion product. We'll get our reaction quotient. So in this example, our ion product, if we were to plug in those numbers and solve, we would get, and again, remember this is squared, we would get an ion product of roughly around 1 times 10 to the negative 20. So that would be our ion product. So now we can compare that ion product to our KSP. Because remember, when these concentrations reach equilibrium and we plug them in, they'll give us our KSP. But we plugged in these current concentrations and they gave us our ion product. So now we can compare our ion product with our KSP and see where the reaction is at. And something important to realize is When in this situation, we see the Ksp is larger than the ion product. So when the Ksp is larger than the ion product, we're unsaturated. So this solution is not saturated yet. It'll keep on dissolving because it's not saturated yet. So these are just things you need to memorize. Whenever the ion product, we took the current concentrations, plug them in and found our ion product, and whenever the ion product is less than the Ksp, we're not saturated. We haven't reached saturation concentrations, so more is going to dissolve. More is going to dissolve, and then eventually we'll reach saturation concentrations, and then once we've reached saturation concentrations and plug them in, we'll get our Ksp, it'll equal our Ksp. But now let's do another example. Let's say we have this situation. Now we have current concentrations. Maybe the calcium, a concentration of 0.0117 molar. So again, we put in a chunk of metal, we let it dissolve, and at this point, the calcium concentration is this. And let's say the hydroxide concentration is maybe 0.023 molar. So these are now our current concentrations. These are our current concentrations. We plug them in and we can find the ion product. The ion product, the reaction quotient under this particular condition. And if we were to solve this, plug this into the equation and find the ion product, now we would get an ion product of roughly around 6.2 times 10 to the negative 6. So now our ion product equals the Ksp. So we know when our ion product equals the Ksp, that means we're at equilibrium. We're currently at equilibrium. These concentrations are the equilibrium concentrations. Because again, we plug them into our ion product equation, and we got an ion product that equaled the Ksp, so clearly these are equilibrium concentrations. So when the ion product equals the Ksp, you're at equilibrium. However, let's say we have a different situation where we just dumped in a lot of these ions. So instead of having a solid and letting it dissolve, let's say we just dumped in a lot of these ions. We dumped in a lot of calcium ions and a lot of hydroxide ions. And let's say now we have the concentration of calcium ions was 0.1 molar. And let's say the concentration of hydroxide ions was 0.1 molar. So we just dumped in a ton of calcium ions and we dumped in a ton of hydroxide ions, and we have concentrations of 0.1 molar of calcium ions and hydroxide ions. Well, again, if we were to plug in these current prevailing concentrations to this ion product equation, we would get an ion product of roughly around, under these conditions, of roughly around 1 times 10 to the negative 3. So under these current concentrations, plugging them into this equation, we get an ion product of roughly 1 times 10 to the negative 3. But we see this ion product is greater than the Ksp. And we see when the ion product is greater than the Ksp, we're saturated. This is a saturated solution, where in fact the concentrations are higher than the equilibrium concentration. So in fact, what's going to happen, this solution's saturated. These concentrations are higher than the equilibrium concentrations, so this solution's saturated with these ions, so now these ions are going to precipitate. They're going to precipitate, forming more solid, decreasing these concentrations, and eventually they're going to keep on precipitating, decreasing these concentrations until we have concentrations at equilibrium, until we have concentrations that we plug in, and they'll give us an ion product that gives us our Ksp, our equilibrium. So there are these three examples to be aware of. If we plug in the current concentration and we get an ion product that's less than the Ksp, we're unsaturated, and therefore the solid's going to keep on dissolving until we reach saturation or equilibrium. However, if we have high concentrations and we plug in those high concentrations and we get an ion product that's greater than the Ksp, we're super saturated. We're saturated, that we have higher concentrations than at equilibrium, so therefore they're going to precipitate to lower those concentrations, and they're going to keep on lowering, keep on precipitating until they reach concentrations at equilibrium.